Hello, A-Beers. And what you see in front of you is the differential equation. Change in quantity over the change in time is directly related to that quantity times some constant. Okay? Now your book may use, instead of Q, that it may use Y. And so we say that we have growth over time if k is greater than 0, and we would have decay over time for k less than 0. And of course, if k is equal to 0, then you don't have change, you have a stagnant, constant situation. And you may be aware that things do change over time. Populations grow and decay. You chemists out there have probably studied radioactive decay. Those are the problems we're looking at in the book. And if you're not careful, you have tooth decay. Some hairstyles change over time also. Many of you are jealous, I can tell. All right, so that's what we're talking about. We're talking about over time measurements. So the question is, well, from this differential equation, can we get a function that we can work with? And the answer is yes. But there's no way I could have taught this when separation of variables, that section really comes after this section, which doesn't make sense to me, because the only way I'm going to show you to get to this function is to separate the variables. All right, here we go. So I'm going to get Q over here. I'm going to divide both sides by Q. I'm going to multiply both sides by dt. And I'm going to integrate. What function gives you a derivative k in terms of t? So that would be kt, right? This would be like a du over u. And I'm only going to use 1 plus c, okay? You could have a plus c over here and a second plus c over here, but I'm going to combine them both. Since it's an equation, we can put them under one constant of integration, okay? And then what we're going to do to get to what u is we're going to e it. We're going to e it. And I'm going to share that special Math Daddy video from many years ago. It's called E It. I'm going to link that in the description. So we end up getting, oh, did I say U? This should be Q. So I get carried away. We're going to end up getting Q equals, well, e to the kt plus c is the same as e to the kt times e to some constant, right? And this itself is a constant. Now, I'm going to tell you right now that it is the initial quantity of stuff that we're talking about here, okay? So this ends up being Q0 e to the kt. So the quantity in time t is given by the initial quantity times e to the constant times whatever the factor of time is. And that, my friends, is our exponential growth and decay model. Now I'm going to clear the board so we can do examples. and then I'm going to rewrite this up top so we have it. One moment. Okay, someone stole my marker. I got another one. So we have Q of t is a function of quantity over time, is our initial quantity, which is time equal to 0, times e to the kt. That's our exponential growth and decay model. Q of t, or as my wife likes to call me, QT. My wife calls me QT. Do you believe that? It was Valentine's Day. All right, so we're going to do a few problems from your book in section 6, section 6.3 on page, where is it, section 6.2? I'm sorry, section 6.2, section 6.2. That should be a 2. Sorry about that. Page 419. We're going to do number 33, and then we're going to do number 36 together. Calculator probably recommended here, or some kind of a utility, okay? Okay, so we need to talk about what half-life is just for a moment. Number 33, they give us an isotope, it's called radium. And they're telling us the half-life is 1,599 years. What does that mean? It means if you have an initial quantity, let's say you started with 1 gram. After 1,599 years, if I plug that in for time, right? I should only have half of what I originally started with. So half-life is the decaying process, okay? So what I'm going to do is solve for k, and then we'll use this shortcut every time so you don't have to solve for the constant every time. So initial quantity, 1 gram. After 1,599 years, we get a half. Now, was anyone there for 1,599 years to verify that this is actually an actual, an accurate measure? Well, I don't think so. We're calling this an approximation. Okay. It's a decay model, so we're using a model. So what I'm going to do is I'm going to take the natural log of both sides, Remember I told you, function composed with its inverse? We keep coming back to it now, don't we? What does this allow me to do? It allows me to get to this expression. How do I know that? Well, I'll write it down for you. Some of you forget. We said that natural log of e to the something is the same as e to the natural log of something. Has to give you something back. Right? So this is that something we're referring to. So what do I get? I get 1,599 equals a half, natural log of a half. So this would be considered our k value. This would be our half-life constant. So There's our half-life constant, okay? It's going to be natural log of a half over the number of years. Sorry, that's hard to read. I can read it. For the half-life to occur, the number of years for the half-life to occur. And that's what your K is every time. So you don't have to go through this process every single time. All you got to do is say, whatever the half-life in years is, take the natural log of a half divided by the years, and you'll get that constant. Now, if you remember at the beginning, I told you that for this to be a decay model, K has to be negative. Well, do you see a negative value here? Well, I think you do. Remember the graph of the natural log function? Remember on natural log graphs? Natural log is the inverse of exponential. It goes through this point 1, 0, right? Because natural log of 1 is 0. So any value to the left of 1, any value to the left of 1, down here, natural log of x is negative, isn't it? So what I'm saying to you is this is less than 1, so this is a negative value. So this is a negative expression, okay? Now I don't have my calculator in front of me, so I would ask you to have it available. I'm just going to allow K to be our constant, and we'll work from there. All right, so we're now able to do problem 33. Let me erase the board.